Assalamu alaikum students. Hope all of you are fine by the grace of Almighty Allah. In our today's lesson, I will discuss about chemical equilibrium and the Lacity Principle. Chemical equilibrium is a very important characteristics of any reversible reaction. Okay, and at first you can imagine you are digging a hole, and as you are digging that hole, your friend is refilling it. Okay, you were digging the hole and your friend at the same time is refilling it, and if you are digging the hole faster than your friend, and the hole gets larger, and if your friend is filling the hole faster than you, uh, then the hole gets smaller. Okay, and but if the two of you are working at the same speed, at the same rate, then there would be no change to the size of the hole. Okay, the size of the hole remains the same. Okay, and the same concept can be applied to the reversible reaction. Okay, sometimes chemical reactions are not unidirectional. Okay, that means they are irreversible reactions. Okay, and they are not irreversible, that means they are reversible, and the reactors produce the products which then go right back and produce reactants. Okay, and this means there is both a forward and backward reaction, that means reverse reaction. Okay, spontaneously occurs a forward reaction and a backward reaction or reverse reaction. Yeah, and that's why this concept can be easily applied to a reverse. If the rate of forward reaction and that means reactants to products is the same as the reverse reaction, that means products to reactants, the reaction is said to be at equilibrium. Okay, and look at these graphs. Okay, and look at these graphs at the start of the reaction. The forward reaction has higher rate. Look at the red curve is the rate of forward reaction, and has the at the initial point when time is 0, then the forward reaction has a higher rate, and it decreases gradually with the progress of time. It decreases gradually, we can observe that easily. It decreases gradually with the progress of time, and again at the start the rate of backward reaction, that means the rate of reverse reaction, this blue color curve remains slow. Okay, remains low. Okay, and but it increases gradually with the progress of time. This increases, this decreases, okay, with the time. And at the stage, this stage, okay, at the stage, both the rates of reactions, both the rate of forward reaction and the rate of reverse reaction become equal, and this state, this point is known as chemical equilibrium, and this is called a dynamic equilibrium. Okay, because both processes are occurring simultaneously, and even though there is no overall observable change, no visible change is observed, it appears that the reaction has stopped. Okay, apparently it seems to be the reaction has stopped, but in reality it has not. And however, in equilibrium, um, we can easily observe from this graph, and this graph is shows the time versus amount, or you can say concentration, time versus concentration and graph. This is also, this red is reactants concentration is high at this point, and when time is 0, at initial point, at the very initial point of the reaction, and then and gradually the concentration of the reactants decreases, and the concentration of products increases. And when at equilibrium, these two at equilibrium, there there is no change in amounts. That means there is no change in concentration of reactants and products. Okay, and this position is known as equilibrium. And for a chemical system, that means for a chemical reaction and to be at equilibrium, it must meet two important criteria. Okay, the reaction one is the reaction must be a reversible reaction, reversible process, and it must be taking place in a closed system. Okay, and a closed system means, and a closed system is one where there is no exchange of matter, only exchange of energy. That means only exchange of heat energy, light energy, etc. can be occurred in a closed system. No, there is no exchange of matter from the container or into the container. Okay, and if we have already learned about that, we have learned how to use stoichiometry to discuss limiting reactants and show how much of products to expect. But these are for uh, these stoichiometry are for only unidirectional reactions. Okay, that means only irreversible reactions, where we assume that all the reactants make products, and then the reaction is over. Okay, the reaction is completely over. Okay, but with equilibrium, from the concept of equilibrium, it's a little with equilibrium, it's a little more complicated to calculate it, the concentration of each substance, products and reactants will be at equilibrium. Okay, and we will learn about that at higher classes. Okay, and now look at this second graph. Okay, we can and this is the definition of we have discussed about the rate of reaction, and this is the definition of rate of reaction: the amount of product produced from reactant per unit time is called the rate of reaction. The amount of product produced from reactants per unit time is known as rate of reaction. Important question: what is the rate? I think it is clear to you is the definition. And look at this graph. Okay, and here we explain the chemical equilibrium using a example. Okay, and this example at equilibrium is the reaction of hydrogen and iodine in a closed container. Okay, hydrogen and iodine both are gaseous substance, and the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide. Okay, produce hydrogen iodide, and at the start of the reaction there is a high concentration of hydrogen and iodine. Okay, this is the this blue curve is shows the concentration of hydrogen and iodine. That means product iodine is missing here. Okay, this represent the concentration of both hydrogen and iodine. And at initial point, at the start of the reaction, there is a high concentration of uh, this point. Okay, hydrogen and iodine, and the concentration decrease as hydrogen iodide formed. Okay, gradually with the progress of time, and the concentration decrease as hydrogen iodide is formed, and the concentration of hydrogen iodide. Okay, this is this red color curve shows the concentration of hydrogen iodide, and the concentration of this product increases as the forward reaction proceeds. Okay, And as hydrogen iodide is formed, the reverse reaction is then able to occur, because for the reverse reaction hydrogen iodide is the reactant. Okay, so uh, as hydrogen iodide is formed, then the reverse reaction is start. Okay, and the reverse reaction is then just then able to occur, and over time, with the progress of time, the concentration of hydrogen iodine and hydrogen iodide remain constant. Okay, and the reaction at this point, okay, this is the time limit. After that, they uh, mm, doesn't change, they do not change their concentration anymore. Okay, and the concentration of hydrogen iodine and hydrogen iodide remain constant after that time, and the reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate. That means the production of hydrogen iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide. Hydrogen iodide decomposes to produce hydrogen and iodine. This rate also the same. That means the forward rate, forward reaction rate, and the backward decomposition of hydrogen iodide rate will be the same. So there are no observable changes, although uh, both the forward and reverse reactions are occurring. The reaction has to stop, it seems. Okay, but actually the reaction doesn't stop. Okay, and that's why it is called dynamic equilibrium. That means these points are dynamic equilibriums. Okay, this time is for reaching the dynamic equilibrium, and the reaction, uh, if the container, the lid of the container was removed, the system is no longer at equilibrium. Okay, as both the reactants, because both the reactants and products, okay, both the reactants hydrogen iodine and product are vapor phase, are in vapor phase. Okay, and so matter would be able to escape the system easily. The reactants, products, and the all the products, all the matters would be able to escape from the system, and then the equilibrium will be distorted. Okay, and then in summary we can say a chemical system is said to be at equilibrium when the rate of forward reaction is the same as the reverse reaction. Okay, if you have to answer the question what is chemical equilibrium, you can easily define like that: a chemical system is said to be at equilibrium when the rate of forward reaction is the same as the rate of reverse reaction. Okay, and uh, next, our this is another example. Okay, and as nitrogen and hydrogen react to form ammonia. This is a Weber process reaction. Okay, the concentration of those gases drops. Look at, this is the forward reaction. As nitrogen and hydrogen react to form ammonia, the concentration of those gases drops, decreases, making them less likely to collide. Okay, we know for react for chemical reaction, the collision of molecules, the collision of reactant molecules is very important. Okay, and when the concentration of the reactant molecules drops, and then they are less likely to collide and keep reacting. Okay, and so the rate of forward reaction slows down. Okay, slows down, and the concentration, and at the same time the concentration of ammonia, okay, the concentration of ammonia rises, and more ammonia molecules are available to break up. For the reverse reaction, ammonia is the reactant, and then the more ammonia molecules are available to break up into the reactant gases. Okay, that means into nitrogen and hydrogen, and the rate of reverse reaction speeds up, and then the rate of reverse reaction speeds up, and the those process reach at eventually those process reach a point where they happen at the same rate. Okay, where the these two process happen at the same rate, and at that point there is no measurable change in the concentration of any gas is point. Okay, there is no measurable change, and we cannot measure the change in the concentration of the reactants and products. Okay, that means nitrogen, hydrogen, and ammonia, and nitrogen and hydrogen keep combining to form ammonia, while ammonia keeps breaking down into nitrogen and hydrogen at the same time. Okay, nitrogen and hydrogen at this point, this equilibrium point, the nitrogen and hydrogen keep combining to form ammonia molecules, and ammonia molecules keeps breaking down. Okay, that means decomposed into nitrogen and hydrogen at the same time, at the same speed. Okay, and that's why they reach equilibrium, and we know for when the balance of some any natural system gets disrupted. Okay, then we say that it's out of equilibrium. Okay, out of equilibrium, and nature usually finds to way restore the balance. Okay, and in science the word for balance is equilibrium. Okay, and equilibrium and balance is the same, similar meaning, and from this we know, and this equilibrium, this chemical equilibrium are dynamic in nature. The reaction basically never stops. It's just that we don't notice any changes at that point, because everything that happens in one direction, okay, that happens in one direction, that means forward direction, is perfectly balanced out by what happens in the other direction. Okay, and that's why we cannot observe the change in concentration in reactants molecules and product molecules, and this is the concept. This was the concept of main basic concept of chemical equilibrium and dynamic, that means dynamic equilibrium. Now, scientist Lacity. Now I will discuss about a very popular principle, Lacity principle. Okay, and this Lacity principle explains how a Lacity principle shows you explains you how a system or reaction at equilibrium does in response to stresses. That means conditions of a reaction. Okay, how to respond to conditions of different conditions of a reactant. And let's return to our original example of you digging a hole. Okay, and your friend refilling it is simultaneously. Okay, and if you start digging at the rate faster than refilling, then the hole gets larger. Okay, if you start digging at the rate faster than your friend's refilling rate, okay, then the hole gets larger, and in order to maintain a constant size, but you want a constant sized hole, then in order to maintain the constant size of the hole, your friend must work harder to fill it faster. Okay, your friend must work harder to fill it faster. And following the same idea, when a chemical system or reaction at equilibrium is stressed, okay, the system works to restore equilibrium like nature. Okay, and is known as Lacity Principle. Okay, when a chemical system or reaction at equilibrium is stressed, okay, then the system works to restore the equilibrium, and we can say the Lacity principle like that. This statement is the at the equilibrium of a reversible reaction. Okay, at the equilibrium of a reversible reaction, if any of the factor, okay, any of the factor, that means any of the conditions, and these conditions are temperature, pressure, and concentration of reactants, is changed, the equilibrium position will shift in such a way that the effect of factor change is neutralized. Okay, the effect of factor change is neutralized. That means the system, the reaction proceeds to restore the equilibrium. Okay, restore the balance, and the stresses and the factors are changes in concentration, and changes to the pressure, and changes to the temperature. These are the three main factors which chemical equilibria can be disturbed by these is factors. Okay, by chemical equilibria can be disturbed by changes in the concentration of one or more substances, that means reactants, and by changes in temperature or pressure, and we describe these changes based on which way they force the equilibrium, they force the position of equilibrium. Okay, and we discuss about that, and we say a change shift the reaction to the right if it tends to make more products. Okay, this is the important point. You have to remember that we say a change shifts the reaction to the right if it tends to make more products form. Okay, and to left to the left shifts to the left if it tends to make more reactant forms. Okay, and obtaining the maximum amount of product from the reaction depends on the proper state of reaction conditions. Okay, that's why it's a very important principle for for industrial chemistry. Okay, because increase and decrease of products in equilibrium of reversible reaction is controlled by the Lachatellier's principle. Okay, and for obtaining the maximum product from any reaction, any chemical reaction, we have to sincere about these conditions. Okay, and we have to choose, we have to maintain the proper conditions for maximum production, and now, at first, I will discuss about the changes in concentration. Okay, the effect of changes in concentration at equilibrium, at chemical equilibrium, and at first let's describe a hypothetical reaction at equilibrium. Okay, and A plus B produce C and D. If we add more product, this is a balanced equation. Okay, this is the equation which is reached at equilibrium. Okay, and if we add more A and B, the system becomes stressed. Okay, the system becomes affected and is no longer at equilibrium. Okay, look at this picture. Okay, we add more reactants A and B, then the system becomes straight and is no longer at equilibrium. Okay, and to counteract the stress according to Lacity principle, the system must have to reach the equilibrium again, and to counteract the stress the system forms more C and D. Okay, more C and D in order to remove the excess A and B. Okay, and then the equilibrium shifts to the right. Okay, you can easily observe, if the equilibrium shifts to the right, then mm, the system and restore the equilibrium again. Okay, from shifting the reactor rate, by increasing the rate of forward reaction. Okay, they can again they can again restore the equilibrium. And as you can see, the equilibrium has now been restored for this case. And if we add more C and D. Okay, look at this picture. Here you can see in that, if we add more C and D, that means if we add more product, then the system becomes straight also, and it is also no longer at equilibrium. You can easily observe. Okay, and so counteract the stress. Okay, it's to minimize the to neutralize the effect of increased concentration of product. We have to mm, then the rate of backward reaction will be increased. Okay, and the equilibrium shifts from right to left. Okay, right to left, and then the constant equilibrium can be gained again. And um, if the concentration of C and D is decreased. Okay, now this is another condition. The last picture, this picture shows another condition, another option. If the concentration of C and D is decreased, as the product is produced, and we remove the products from the reaction vessel, then the system also is stressed. Okay, we can easily observe that from this picture, and no longer at equilibrium. And to counteract, to minimize this stress um, of removing the constant product, that means decreasing the concentration of product, more C and D are also produced. Okay, again produced. So equilibrium shifts to the right here, from left to right here. That means, by changing the concentration of products or reactants, we can change the position of equilibrium. Okay, from left to right or right to left. Okay, and the target is to restore the chemical equilibrium. Okay, and reach the equilibrium point. Reach the point where the rate of backward reaction and the rate of forward reaction is equal, are equal. Okay, and when the constant, next, look at this pictures. We can take an example. Okay, Haber process. Okay, I can you can remember that the Haber process. Once the Haber process for ammonia. Okay, the Haber process for ammonia production is at equilibrium. This is the equilibrium. The first picture shows you the is at equilibrium. The nitrogen, hydrogen reacts to produce ammonia, and this reaction reach the equilibrium. And if we add at this equilibrium point, if we add more nitrogen gas to container, the existing hydrogen would have more nitrogen to react with. Okay, we add more nitrogen to it. Okay, no, nitrogen or hydrogen to it, then the concentration of reactant, that means the amount of reactants will be increased, and the equilibrium will be distorted. Okay, and thus and then the nitrogen and the hydrogen reacts with each other and produce ammonia, and sending the reaction to the right side. Okay, until the reaction balances itself again. Okay, again, that means the reaction balances itself again. Okay, and removing some of ammonia would have the same effect. If we remove some ammonia from here, then and the structure, the equilibrium, and the position of equilibrium will be the same as this picture, like this picture. Okay, and then also there will be less ammonia available to break down, and that's why the rate of forward reaction will be increased. That means nitrogen and hydrogen reacts with each other and produce more ammonia to balance this is chemical reaction. Okay, to reach the chemical equilibrium for this reaction, and thus the balance is restored. And now the effect of I will discuss about I will discuss about the effect of temperature and pressure on chemical equilibrium in our next class. That's all for today, students. Assalamu alaikum.